Hello folks. Alright, this time around I want to look at templates and some of the templated libraries specifically for C++, but the general idea is that we want to be able to describe a class or a function, an abstract data type if you like, and not specify a data type for it. Essentially leave just a name where the real variable, where the real data type is going to go in whatever it is we're defining later on. The idea is, if I create a swap method or a swap function without specifying the type, just put a t in where the type is going to go, that's providing a blueprint for the compiler so that when it sees a swap routine later on, it can look at the blueprint that you gave it for swap routines and look at the data type that's actually used and build the correct version of a swap routine from the blueprint and the data type. So this is the notion behind the templated types. You only write the code once, and it gives the compiler the instructions so that it can build the right versions of your routines later on. So that's the notion. We'll see how well we can get this to function. And again, we'll look at this specifically for C++. So there is actually a standard template library, it's usually referred to as the STL for C++, that provides a huge variety of abstract data types in this templated form. So for stacks, for queues, for lists, for vectors, for sets, there's a ton of these available. And so we can use these and specify, okay, this time around I want a stack of ints, or this time around I want a stack or a list of ints, or this time around I want a list of floats or a stack of strings or whatever it might be. So we tell the compiler what we want built. It goes back to this library of templates, finds the blueprint for a stack or for a list, and fills in the right data type and then compiles. So these are pretty robust. It's often a much better idea to use the STL for a list or for a stack or for a vector rather than continually rebuilding your own versions of them. Obviously they won't be customized to do exactly what you want, but they're pretty flexible and pretty robust. So I will encourage you to use these. We'll practice some in just a little bit, both with creating our own templated types and with using the STL. So for creating our own, basically we have to tell the compiler that something is a template and write this blueprint for it. And then later on there's got to be a way for the compiler to figure out when to fill in one of these templates. So the idea is to tell the compiler that the thing coming up is a template or a blueprint. We use the word template, and then T is going to be the name that I'm going to use for my unknown data type, my abstract type if you like. And you can either use class, there's a couple of keywords we can use in here. I'm going to use class, so template, and then in the angled brackets class, the name you want to use, and then you write the routine that you're interested in. And this can be a class definition, it can be a function, it can be a method, but you write the beast using T, the name you specified here, wherever the data type would have gone. So here I'm saying here's a template for a swap routine where they're passing two items by reference, both of this anonymous type T. We're going to create a variable also of type T, copy X into temp, Y into X, and temp into Y, the usual swap idea. So when the compiler sees something like swap X and Y or swap user1 and user2, it checks to make sure they're both of the same type and then builds a version of swap from that data type and the blueprint. So of course this is only happening when the compiler actually goes through and compiles your code. So it looks at your code as it's compiling, looks at the data types you're using, looks at the blueprint for swap, and builds the right beast. So if the compiler sees it, it'll build it. You can also tell the compiler in advance, by the way, I want you to build a swap of this particular type. So, after you've thrown in your template or your blueprint for swap, you can actually tell the compiler, I want you to build a version of swap for ints. So the way you do it is to say, template, and then the profile for your function with the data types filled in, and with the data type you're specifying for swap using the angled brackets. So I'm saying I want to build a swap for int, and therefore the parameter list is going to look like this, a couple of ints. You know, it's possible that your templated type might be part of the return type as well, but yeah, that's the idea. So the compiler can either build something when it sees it, or you can explicitly tell it in advance, I need you to build one of these because I am going to be using it. Now, it does bring up some issues in terms of separate compilation. So suppose I put my blueprint, my template for swap, I put just the profile for it in swap.h, and then the full blueprint for it in swap.cpp. So the compiler can go off and compile that separately. All right, and it, you know, we do our g++-c, and it goes off and compiles this, and it's got this little .o file. But at that point, when it's compiling that, it has no idea what data types you're actually going to use swap with. And then somewhere else, you've got the you know, some code.cpp that's actually going to do a swap. So it includes swap.h, and we compile that on its own. So we compile swap or we do our g++-c some code.cpp, and it creates our some code.o. But in here, all it sees is the profile in swap.h. It doesn't see the full version, the full template in swap.cpp, and therefore it can't actually build, let's say, the int swap or the string swap that you were using in some code. So this compiles okay, but it doesn't know that there is no int version of swap or no float version of swap or no string version of swap actually built. So each of these two things compile fine by themselves, but then when we go to link them together, it doesn't work. It'll sit back and say, oh, there's no definition or no implementation of, you know, a swap int. So here we'll get a link time error. And this is one of those situations where it's handy to be able to do things like, say in advance, build me one of these. So there's a couple of solutions to the separate compilation problem. Again, in swap.h or in swap.cpp, we could put in a bunch of explicit instantiations where I say, build me one of these, build me one of these, build me one of these. But it's not very flexible, right? If later on I suddenly decide that I also need a swap for some other data type, then I have to go back in, edit my swap.cpp or my swap.h, put in the new explicit instantiation, and recompile it as well. An alternative is, instead of putting the blueprint, if you like, for swap into the swap.cpp, we put that whole template in swap.h. So effectively there is no swap.cpp as far as, we don't need a swap.cpp. We're putting the whole thing in swap.h. Then when you include swap.h, you're including the blueprint for how to build swaps. And so anytime somebody compiles something like their, what did I call it here, our sumcode.cpp, when they compile that, it's included the blueprint, so it's got the blueprint available to work from. It sees that you're using a swap, it builds the right version. So that works. It just has the downside of your full implementation of swap is shown in the header file, which people are going to be able to take a look at. So if there's implementation details you wanted to hide, you're kind of losing that. But it does function. All right, I just wanted to play with some of those a little bit and make sure that we're okay here. Where did I put this? Let's go into our templates. I think that's where I put this. So in this one, we've got, I hope, okay, in this case we're actually doing a templated class. So I've got some kind of a data store class that's just going to let us store a bunch of data values of some type. And again, this is going to be our templated type, so that I want to be able to create a data store for ints, or a data store for floats, or a data store for strings. So in the header file here, I'm going to provide the definition of the class, but with this type unspecified. right? My template, I'm going to use T for my type, and all I'm going to do is stick these things in an array that I declare dynamically. So, the data store's got an int to keep track of how much space has been allocated, keep track of how many have been stored so far, and then a pointer so that we can actually allocate the array of whatever data type we've got. Allocate my array of ints or my array of floats or my array of strings. A constructor that'll just build the thing, a destructor to deallocate the array at the end, an insert so I can insert a new item of type T, and a print just to print them all out. So again, we just say, okay, here's my templated class. It gives the compiler the information to build one if it needs to. And if we take a look at our data store.cpp, so in here, we're going to provide the templated version of each of the methods for the class. So a templated version for the constructor, and you'll note that for each of these things, the name of the class is data store and whatever data type it happens to be. So you're going to use this open and close angle brackets and the type name that you're using. So data store of some type, a data store of ints or floats or whatever. Again, the compiler is going to fill that in and say it's a data store of ints or it's a data store of strings. And the method that we're introducing, here's the constructor. And again, we're just using the type in there as if it was a real type, just using the name T as if it was a real type. And the same thing for each of the other methods. Right? For the destructor, we're saying, okay, here's a template for the destructor. Here's a template for the insert. And again, all these things are doing is adding it to the end of the array. A template for the print. And since I'm doing this with separate compilation, and since I've got the implementation in the .cpp file here, I'm actually going to tell it, okay, I want you to build an instance of this class for floats and another one for strings. So I'm going to do the explicit instantiation where I say, build me, so you use template, class, and then the name of the class you want built and the data type to use for it. I want you to build me a data store of floats. I want you to build me a data store of strings. So it's going to implement each of these classes, or implement the class with each of the methods. So we'll have a print routine for a data store of floats. We'll have a print routine for a data store of strings. And then when we go to use it, you specify, okay, I actually want to use one of these things. I want to use a data store of floats, and you pick your variable name. I want to use a data store of strings, and you pick your variable name. And then you can quite happily call the methods, right? Everything works normally after that. It's just when you create your variable, you have to specify, I want to use the templated type, and this is the data type I want you to build it based on. And the rest of this is just going through and saying, okay, let's try it out. Let's try a couple of inserts into the floating point version and then print it. Now we'll try a couple of inserts into the string version and then print it just to see if it works. Ignore the swap comments for a second there. And then hopefully I actually did provide a makefile. So we'll try running this, and it does actually work, right? It's gone through and built and used our stores for floats and for strings. The other one I wanted to mention there was, where are my files? In prog-h, we provide the other approach I was talking about, where we put the full implementation of something, of a templated class or a templated method or a templated function, into the header file and then just hash include the header file. Right? So in this case, here's the swap routine again in prog.h. And so in prog.cpp we include it, and then when the compiler goes through to compile prog.cpp, it looks in the header file, sees the blueprint for how to build swap, builds the version that we actually use here, and we can actually just go ahead and use swap. The compiler sees this, says I need a swap, what data type are F and G? They're both floats, good, they're the same type, so I know how to do this, and so it builds a float version of swap. And so that was the other part of the run of progx, where it actually shows that, okay, here's what f and g were before the swap, and sure enough, after the swap, it did actually swap them. So again, the templated types, we can create our own, or we can use some of the C++ provided template types. Now, we're going to come back and talk more about the standard template library next time around and look at iterators in it, and we'll play with some other bells and whistles next time.